Time to start the class. Hello, my dear students. I hope you're all doing well. My name is Benatang Paton, and I welcome you to the channel Classroom, where we learn together. So, today's class will be a continuation from the previous video, which was about solenoid. In today's class, we'll be focusing on the applications of a solenoid. And then there are two very important applications of a solenoid. Okay, we use a solenoid to make permanent magnet and a temporary magnet. So we'll focus on that. Okay, so without wasting further time, let's jump into the topic and let's learn together. Okay, so grab a notebook, a pen or a pencil, and please take down the notes, because this will serve as a very handy and very useful notes during your exam or even during tests and all that. Okay, so that is what I always tell to those who are regular tuners, and if there is anyone new, then always develop this habit. Okay, this habit is very important and very useful, especially for a student. So an electromagnet. Okay, well, we'll be talking about an electromagnet. Okay, so a solenoid, I should be saying a solenoid. So you know a solenoid, isn't it? A solenoid is a wire having many turns in which current is made to pass through. Okay, one side is plus, the other side is negative, and if current enters from the so the side from which, okay, the end from which the positive terminal of the solenoid is connected to the battery is considered as the south, then the other end will be considered as the north. Okay, and since we have south and north poles, magnetic field will be produced, and this behaves like a bar magnet, or this gets magnetic properties. Magnetic field lines are generated, and that's how a solenoid behaves like a magnet. Okay, it can be a bar magnet, it can be a horseshoe magnet. It will behave like any type of magnet. Okay, now in today's class we'll be talking about the core of the solenoid. Focus will be given to the core of the solenoid. So our today's discussion is entirely based on the core. Now, currently, if I ask you what is the nature of the core, or what is inside the core of the solenoid, the answer is empty. The core of the solenoid is hollow. There is nothing inside the core of the solenoid. It's hollow. Remember, class, by default, a solenoid has got air core. Okay, air core. Air core. How does it get an air core? Because it's empty, nothing is there, so it's air core. So you can actually see through. It's air core only. Okay, so by default, okay, air core, that means the core of a solenoid is empty, khali hai, andar mein kuch nahi hai. Okay, khali hai. So now what we do is we will change the nature of the core. Okay, but how do we change the nature of the core? By inserting, okay, two types of iron. We can either insert a hard iron or we can insert a soft iron. So anyhow, we are inserting an object, and now this is our discussion today. So I have just inserted an object. It is an iron. Okay, it can be a soft iron, it can be a hard iron. If it is a hard iron, we'll discuss what it gives us. If it is a soft iron, then we will also discuss what it gives us. But it's definitely iron. Okay, so let's discuss the applications of a solenoid in detail. So let's go deep into our topic, applications of a solenoid. So generally a solenoid gives us two major applications. Okay, we use a solenoid to make permanent magnet and hard magnet. So number A, making permanent magnet, and number B, making temporary magnet, which is also known as an electro magnet. So we will be studying in detail about an electromagnet. Sorry, my spelling is wrong. Electromagnet. Okay, so these are the two useful applications of a solenoid. using a solenoid, we can make permanent magnet. Okay, so let's discuss in detail about permanent magnet. Permanent magnets. Permanent magnet. Let's talk in detail. The first question that I want to ask you is, have you seen a permanent magnet? Have you held a permanent magnet? Have you touched a permanent magnet? Have you seen one? If you have seen one, tell me, where have you seen? Where have you seen? Yes, of course you have seen a magnet. Okay, that blackish, round, most commonly it will be round, okay, like a donut. Okay, black. Okay, that round. But where did you see this one? Where did you see this typical cylindrical, this round circular magnet? Where did you see that? Yes, you have seen it inside the TV speakers. You have seen it inside the woofers. You have seen it inside the speakers. You have seen it inside every audio devices. Okay, radio, whatever it may be. Okay, even inside the phone. Okay, even inside the phone. I don't know what to say, but even inside the phone, we have speakers present inside it, and they are all using magnets. The black, okay, the black cylindrical thing. Okay, so don't you want to know, like, how are they made? How are they made? And what are they called? These are called permanent magnets. You know why they are called permanent magnets? Because they do not lose their magnetic properties. They do not lose their magnetic properties. Okay, that's why they are called permanent magnet. They are called permanent magnet because they retain their magnetic properties for a long, when I say long, a very, very long period of time. Okay, so that's why they are called permanent magnet. So the magnets that are present inside the audio speakers, they don't lose their magnetic properties. So we are going to learn about it. This is one of the applications of a solenoid. So how are they made? They are made by inserting hard iron. Okay, by inserting hard iron. When the core of the solenoid is, okay, made of hard iron, then we get ourselves permanent magnet. Okay, so let's discuss in detail. So permanent magnet, if a hard iron is placed, let's erase this one and make more room inside the core of the solenoid, and current is made to pass through for a long period of time. The hard iron becomes a permanent magnet. This is it, my dear students. This is the story of a permanent magnet. If a hard iron is placed inside the core of the solenoid, so let this be the hard iron. So a hard iron is now made the core of the solenoid. Okay, and current is made to pass through. So current is traveling here. Okay, current is traveling here, and then current will exit out. So we have current traveling, and current is made to pass through the core, okay, through the hard iron for a long period of time. Remember, okay. Now here, the reason why they don't lose their magnetic properties is because we're using hard iron. Now here I want to tell you that a hard iron, okay, does not easily become magnetized. I repeat, a hard iron does not easily become magnetized, and since it does not easily become magnetized, once it becomes magnetized, once once it attains magnetic properties, it doesn't easily lose it again. I hope you all followed. A hard iron does not easily become magnetized, and once it becomes magnetized, it does not easily lose its magnetic properties. So this is the catch. Okay, this is how we're able to make a permanent magnet, and this is possible only with hard iron. Okay, now this hard iron, examples of hard iron. Okay, examples of hard iron. What are these hard iron? Hard iron. So examples of hard iron are, we have nickel, okay, cobalt, and steel. So if this is made of nickel, okay, or it's made of cobalt, or it's made of steel, okay, then this will give us a permanent magnet. So when the core is made up of nickel, okay, when the core is made up of nickel, cobalt, or steel, if we use nickel rod or cobalt rod or steel rod, okay, as the core of the solenoid, and allow current to pass through it for a very long period of time, then what will happen? This copper rod, this cobalt rod, okay, this steel rod, and this nickel rod, what will happen? They'll become magnetized. This nickel rod will get magnetic properties, okay, this steel rod will get magnetic properties, and then it will start behaving like a magnet, and it will not easily lose its magnetic property. You know why? Because in order to make it in order to let it attain magnetic properties, we have to let current pass through for a very long period of time. Okay, so once it attains magnetic properties, it does not easily lose it, and this is the reason why they are called permanent magnet. The word permanent is there. Remember this, permanent. Okay, permanent means it is there to stay for a very long period of time. So permanent magnet, we can only make it by using hard iron. So what are examples of hard iron? Nickel, cobalt, and steel. These three. Okay, so I hope it's clear. So this is how the woofer speakers are made. The speakers in every audio system is made. Okay, radio, tape recorder, everything. This is how it is made. Okay, so let's go to the next one. Now we'll learn about temporary magnet. Okay, so let's learn about temporary magnet now. Point number B. Now we will be using a soft iron, so let me change this also. Next, point number 2, or point number B, temporary magnet. Temporary magnet, which is also known as an electromagnet. Okay, also known as electromagnet. Also known as electromagnet. Remember this. So let's write down the definition, or let's write down some points about it. When a soft iron is inserted and is met the core of the solenoid, we get ourselves a temporary magnet called an electromagnet. So when a soft iron is inserted and is made the core of the solenoid. So now this is a soft iron. So now the core is made of soft iron. So when a soft iron is inserted and is made the core of the solenoid, we get ourselves a temporary magnet called an electromagnet. Now why is it called a temporary magnet? Temporary means, okay, for a brief period of time. So we get a magnet, okay, which will behave like a magnet for a brief period of time or a brief amount of time. Okay, so when will it stop being a magnet? Okay, when will it stop being a magnet? When will it lose its magnetic properties? Imagine this is a solenoid. Imagine that this is a electromagnet. Or let's go here. So this is an electromagnet, okay, because we are using a soft iron core. So when will this electromagnet lose its magnetic properties? When will it stop behaving like a magnet? So when the flow of current stops. When no current flows through the solenoid, then okay, this will stop behaving like a magnet. That means this will show magnetic properties only when current is passing through the solenoid. When no current passes through the solenoid, that means if we shut off, if we close, okay, if we stop the current flow through the solenoid, then this will just be an ordinary piece of iron only. Okay, that means this will not show magnetic properties. It will lose its magnetic properties. This is the reason why it is called a temporary magnet. So it will only exhibit magnetic properties as long as current flow is taking place in the solenoid. The moment the current flow is cut, this will stop behaving. All the magnetic, okay, this will lose its magnetic properties. The soft iron will stop behaving like a magnet. Okay, so this is it. That's why it is called a temporary magnet. Okay, so let's write down this point. Let's write some input. Put the star and electromagnet behaves as a magnet only when current flows through the solenoid, or you can also write wire. Okay, only when current flows through the wire, which is the solenoid. Okay, the wire is made in the form of a loop curl. Okay, so it is a solenoid. So an electromagnet behaves as a magnet only when current flows through the solenoid. Okay, next point. When no current flows, okay, then no electromagnet. Very important. When there is no current flow, when the current flow is not there, when there is no current flow, then this will stop being an electromagnet. So remember this, my dear students, that an electromagnet is a temporary magnet. It will show magnetic properties. This soft iron core will behave like a magnet as long as current is passed through the wire, as long as current is passed through the solenoid. Okay, but when the flow of current is stopped, when you switch it off, then the magnetic properties which it was showing will also stop. Okay, now why is it called a temporary magnet? And also, how come a soft iron shows temporary magnetism and a hard iron shows permanent magnetism? So I have already explained to you why a hard iron shows permanent magnetism. It's because it takes time. Okay, it takes a lot of time to become magnetic. So when it becomes magnetic, finally it retains its magnetic property for a long period of time. Whereas in case of soft iron, it is not so. It's actually the exact opposite. Okay, to magnetize a soft iron is very easy. It's very quick. It happens very quickly. It happens very quickly. That's why when current starts flowing, okay, through the solenoid produces magnetic field. Okay, and then now the soft iron core. Okay, now the magnetic field will pass through the soft iron core. Okay, now the material of the soft iron core, okay, gets easily magnetized. Okay, the material of the soft iron core gets easily magnetized. It's quick to magnetize. So what happens? It quickly behaves like a magnet. But just like it quickly became, it could easily magnetize. Also, when you switch off, okay, when you switch it off, again it loses its magnetic properties. That means the particles, the atoms are not able to, okay, hold on to their magnetic properties. So too quick to become magnetic and also too quick to lose magnetic property. This is what happens. This is what happens in an electromagnet. So in electromagnet, this soft iron core is easy to get magnetized, and at the same time it is easy to lose its magnetic properties. So I hope it's clear. This is the reason why it's called a temporary magnet. So solenoid can be used. A solenoid gives us two major applications. It helps us make permanent magnets, which are very useful for us, and it also helps to make temporary magnets called electromagnets, which are also very helpful for us. Okay, electromagnets are very helpful, my dear students, because see, it is not easy to make a magnet the size of this room. This room is say 11 by 13-14 feet maybe. Okay, so it's not possible, it is not feasible, and it is not even convenient to make the magnet the size of this room. Okay, so it is very inconvenient to make big magnets. But we don't need to make big magnets also. We have an electromagnet, isn't it? So when you need, okay, when you need a big magnet, use an electromagnet. Okay, and we are using these big magnets to lift up containers from in the ports. If you go to the ports, you will see cranes fitted with electromagnet, and then they are lifting up these containers from one ship to another ship. Okay, that's how they are doing, how they're able to transport the cargo from one container to another container. So this is done through electromagnet. So we are, okay, so we are using electromagnets to good usage. It's very useful for us. Okay, so remember, making a big magnet is not easy. It's difficult. Okay, it's very difficult also. And where do we store it? Okay, so there are many difficulties with making a big magnet, but we have an electromagnet. So when you need it, okay, use it. When you don't need it, switch it off. It'll just be a normal metal, isn't it? Okay, so this is the advantage of electromagnet. Okay, it's a very useful, okay, very useful thing for us. So this is it. Okay, my dear students, so let's discuss more about the electromagnet. Okay, so let's discuss now the factors, okay, affecting the strength of the electromagnet. Let me erase this now, everything, and we'll discuss the factors which affect the strength of the electromagnet. That will be the next topic. Here, factors affecting. This is important. This is important for exam. The strength of electromagnet. Let me write EM in short. The first factor, number one, number of turns. Number of turns. What does it mean? Now, a solenoid has got turns. The wire has got turns. So let's take a solenoid having 1, 2, 3, 4, 5 turns. And then the other solenoid having 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This has got 10 turns. This has got 5 turns. This is solenoid A, solenoid B. Let's make it an electromagnet by inserting a core. So core is here. Core is here. Okay. So which electromagnet will have stronger magnetic field? Electromagnet A or electromagnet B? Pick and tell me, class. Which electromagnet will have stronger magnetic field? A or B? Correct. It's B. B has got stronger electromagnetic field. Okay. The magnetic field in B, electromagnet B, will be stronger because the number of turns is more. So number of turns. The strength of the magnetic field produced in an electromagnet depends on the number of turns. More number of turns, stronger current, more magnetic field. Okay, more number of turns, more magnetic field, not stronger current. More number of turns, more magnetic field. Remember this. So magnetic field is stronger here. Okay, so magnetic field is stronger here. Or we can also write magnetic field is directly proportional to turns. More number of turns, more magnetic field, stronger magnetic field. Next one, point number 2, it is current in the coil. Current in the wire or coil, okay, anyone. So let's draw again. So 1, 2, 3, 4, 5. Let's make 5 turns again here. 1, 2, 3, 4, 5. Okay. Let's take our electromagnet. Okay. This is electromagnet A, electromagnet B, and then current in the coil. Let's say in electromagnet A, let's say in 1, let's start from B. Okay. Let's say I current is flowing and I current is coming out. Here, 2I is current is 2I. Now you tell me, where is more current? Electromagnet A or electromagnet B? Correct again. More current is in electromagnet A. 2I is not 2I. This is I only. So this is twice the current flowing in B. This is I. If this is 10, this is twice the current flowing in B, which will be 20. Okay, assuming that I is 10, this will become 20. 2 tens are 20, isn't it? So 2I, that means more current flowing here. More current flowing means more magnetic field, means stronger magnetic field. So magnetic field is stronger here. Okay, so magnetic field is directly proportional to current. Okay, more current, stronger magnetic field. So the electromagnet A is stronger than electromagnet B. Okay. Then number 3, length of gap between poles. Length of gap between poles. Now, what does this mean? Let's try to understand. So let's take 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Assuming current to enter from here, this is the positive terminal and this is the negative terminal. This becomes our south, this becomes our north. And then let's take another solenoid or a coil and let's keep the turns closer. 1, 2, 3, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. So here the winding, the spacing is closer. Okay. The number of turns is same only, but they are closer. Okay. And then assuming current to enter from here, assuming this will be plus, exiting from here, which will be minus. So this is south, this is north. We know this is not. So this is the core. Now, the distance between the pole, it's bigger, so let's write D here. The distance between the pole is smaller, so let's write smaller d. So more distance here. The length of gap between the poles. So now from this pole to this pole. Okay, or you can even take into consideration this one also. Okay, here also here also the gaps here. You can see here the gaps are less. Okay, here the gaps are bigger, and the overall length also you can see. The number of turns is same only, but then check out the length of the gap between the poles. Okay, so tell me, who will have stronger magnetic field? Stronger magnetic field will be produced in which electromagnet? A or B? Which are you picking? My dear students, tell me your pick. How many for A? Raise your hand. How many for B? Raise your hand. Okay, I see more hand for B. Yes, correct. You're correct. So B. Okay. B has got stronger magnetic field. Magnetic field produced in B will be stronger. So electromagnet B is stronger. Okay. Remember this. So this will produce stronger magnetic field. Okay, greater magnetic field. So B has got stronger magnetic field. So the magnetic field of B is greater. Remember this. Okay, magnetic field is stronger in B, electromagnet B. So these are the factors which affect the strength of an electromagnet. I hope you all understood. Okay. Now let's do one question which is very, very important, and it has been asked as MCQ, and it has been asked in board exams. So let us discuss that question. It's about a solenoid. So let us do that question together. So let me draw a solenoid here. 1, 2, 3, 4, 5, 6, 7. Let there be 7 turns. And then let me show you the magnetic field. The magnetic fields are here. Then now let's indicate some points. So let there be a point here. Let's call it point A, and let this be another point, point B. Let there be another point here, point C. Let there be a point here, point D. Let there be a point here, point E. And let there be a point here, point F. What is the question? The question is compare the magnetic field strength at points. So we are to study the magnetic field points, the magnetic field strength across these points, okay, at these points. So at point A, let's find the magnetic field strength at point A, then at point B, at point C, at point D, at point E, and finally at point F. So let us study the magnetic field on these points. So let's first start with point A, okay, point A. So point A, observe point A carefully. Point A is an internal point, okay. Point A is an internal point. Now, if point A is an internal point, then what about point B? Is point B also an internal point? Is point B also an internal point? Yes, both point A and point B are internal point. So remember, both point A and point B are internal points. Internal points. Since both point A and point B are internal points, the strength of the magnetic field at point A and point B will be same. Okay, so the strength of the magnetic field at point A and point B will be same. Why? Because they are inside the core of the solenoid. Okay, and inside, you know that the magnetic field lines, they run parallel, no? They go parallel. Okay, they go parallel. So the magnetic field, the strength of the magnetic field at points A and point B being internal points, they'll be same. Okay, remember this. So they'll have same magnetic field strength. Comma, because they are both internal point. Because both are internal points. Now let's move on. Now let's study at C. Now let's study at point C. So point C is not an internal point, whereas, okay, but rather point C is an endpoint. We call it an endpoint. Endpoint. Because these are the ends, isn't it? This is one of the end, and then this also. Then point F also. Point F also becomes an endpoint. So both point C and point F are endpoints. Okay. Then what is the story of the magnetic field at the endpoints? Remember, class, that the strength of the magnetic field at the endpoints is half of the strength of the magnetic field at the internal points. So the magnetic field here will be half of the magnetic field, okay, which is found in A and B. Remember this. So magnetic field here, strength of the magnetic field here at point C and point F, because they are endpoints, their magnetic field will be half of the value or half of the magnetic field at point A and point B. That means half of the magnetic field of the internal points. Remember this, okay? So it will be half of internal, just write internal points. So the magnetic field at point C and F will be half of the magnetic field at internal points. Remember this. So if we say that the internal points are carrying a magnetic field strength of 10, then at C and F it will be half, isn't it? That means it will be 10 ka half, which will be 5. So it will be 10 ka half, which will be 5. I hope you are able to follow. Then let's go to D. So D is here. Okay. Now D is a point above the magnetic field. Okay, above the solenoid. Okay, D is a point above the solenoid. And similarly, look at point E. Point E is below the solenoid. Point D is above the solenoid. Point E is below the solenoid. So here both point D and E, okay, both are points above, okay, and below solenoid. Then what about this? What about this? Just because there are points above and below the solenoid, okay, what about them? What about them? See, now look at point D and look at point E. You will not see any magnetic field here, okay? No magnetic field lines. No magnetic field line, that means no magnetic field strength. If there are no magnetic field lines, then there will be no magnetic field strength. Okay, remember this class that points immediately above the solenoid and below the solenoid, okay, this is a dead zone. There are no magnetic field lines here. Okay, but you will find magnetic field lines here. There will be magnetic field line here. Okay, you will find magnetic field strength here. You will find magnetic field strength here. Why? Because you have actual magnetic field lines here. Similarly, okay, if you go a little higher, then you will find magnetic field lines here. That means magnetic field strength is here. You have magnetic field lines here. That means magnetic field that means magnetic field is here. Okay, so magnetic field strength will be here. But at point D and point E, since there are no magnetic field lines here, this is a dead zone. That means magnetic field strength here is 0. So remember this. So here, okay, what do we write? Yes. So here, no magnetic field lines. No magnetic field lines. So 0. Magnetic field strength will be 0. Okay. Both are points above and below solenoid, and points above, okay, immediately above and below the solenoid, they don't have magnetic field lines. Since they don't have magnetic field lines, the magnetic field strength will be 0. I hope it's clear. Okay, so let's just make a table here. This is inside, okay, inside the solenoid. Then this is what do we do? Let's write here endpoint. These are the endpoints, and this will be points above or below. Then let's say, okay, so if we say that the magnetic field strength inside is B, then at the endpoints it will be, when it was 10, it was half of 10. If the magnetic field line inside the magnetic field strength for the inside point is B, then endpoints will be how much? Yes, B by 2, no? B by 2. Okay, and what about the points above and below? It will be 0. Okay, so if we are to arrange in increasing order, okay, who has the strongest magnetic field here? If we are to show the strength, okay, then we'll have the strongest magnetic field here. The inside points will carry the strongest magnetic field, okay, followed by the end points, and finally 0 here. Okay, so this is my class. Okay, my dear students, this is everything about solenoid, okay, and electromagnet. It's complete. Okay, electromagnet and solenoid, we are completing from this video. Okay, so everything has been explained in detail, and this is very, very important. This will really create a map, a brain map for you, which will help you understand what is actually happening inside a electromagnet and a solenoid. Okay, so before we disperse, I have a question for you. So the today's question is a magnetic field exists around. So the options are, what are the options here? We have iron, we have copper, we have aluminium, and we have moving charges. So this is an MCQ, my dear students, and I want you to give me the answer. I want you to comment the answer in the comment box. So kindly comment the answer in the comment box. Your participation motivates me. Your participation lets me know that you are following. So I will request you all to participate, okay, and keep me motivated and keep me going. So thank you class for tuning in and watching, and I'll see you again in the next video. Until then, you all take care and God bless you all.